Okay, my wonderful students, welcome back. It's been a couple weeks actually since I've seen y'all. I'm happy to see everybody here. And I'm really happy about this. UCF going to March Madness. Look at that basketball player. I love this photo. He looks so happy. Can you imagine? I just love that. Anyways, go get him, UCF. See how that goes. Um, SI schedule this week. Office hours tomorrow, of course. SI today, 2:30. Tomorrow at 3, as always. I want to go over with you some stuff about exam 2. One of the things that I did, get your clicker ready. Actually, I need a little bit of light up here. Okay. Um, One of the things that I did was create an error list for everybody. Now, it looks different from a Scantron printout, which I gave you on exam 1, but it's equivalent in that you can see which items that you got wrong. Now, what you do is you go into your grades page, and over here on the far right, there's a little icon over here, and you click that baby, and you get an error message. And so it'll look like this, and a list of 3-digit codes. And those are the ID numbers internal to web courses for each question. And some of them are matching, and you'll see that on the blurb sheet. But so if you had, like -7, you might have had only 3 items on your error list because the matching, of course, is more than 1 point. So if you miss more than 1 on the matching, you'll still only get 1 error code for that. So, but anyways, this is what you want to look at. So for instance, this student named Bob has 281, 663, 668, and 654. So what you then do down here, you make a note of that stuff, and then you go look it up on the blurb sheet. Now the blurb sheet is already up as well on the blurbs page for exam 2. It's a little bit different, but it looks like this. And so you look up, for instance, 654. So it's a way of making kind of a little mini study guide for the final. So in other words, if 654 is on your error list, then you go and look it up. Path increment, negative work done by gravity. So that's what you got to study, or one of the things you got to study and restudy maybe for the final, so you can crush the final. All right, now I got an iClicker question for you about the final, if you please. And here it is. So go ahead and get onto the system. Let me get my cursor back over here. Okay. And answer this question. All right, 20 seconds to vote. I mean, this should be like really easy. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Stop. And yeah, most of you guys got it correct. Now, just a little bit of test-taking strategy here. Eliminate the ones that you can eliminate if you know that they're absolutely false. What's wrong with C? C is not the right answer. A is the right answer. Most of you got that. What's wrong with C? Yeah. No, I do that sometimes. What? No, right here. There's no April 31st this year. So just mark out your April 31st. All right. And actually, not only this year, but every year, there's no April 31st. So don't let me trick you on that one. Another one, July 4th. Yeah, that's summer. So, it's not going to be in the summer. And this exempt, no, nobody's exempt from the final. Although it used to be, I sometimes did that in earlier semesters, but not anymore. So everybody has to take the final. All right, now this one here definitely is going to happen. I mean, there is a final. Nobody's exempt, and it happens. Oh, wait a minute. That's tempting, isn't it? But the actual answer is up here. It does happen 10 a.m. to 12:50, Tuesday, April 30th. Now, I believe that's the last day of finals week. So sorry about that. We got to go all the way through finals week to this one. And it'll be just like a midterm, double the size of a midterm, but you'll have 3 times as much time. You have 2 hours and 50 minutes, almost 3 hours. That's pretty much double what we have for a midterm. And but you have to be here at 10. All right. And if you get here, if you think, oh, 10:30 class, 10:30 final, you're going to be late. And the problem with that is there's probably going to be someone in here that if we start at 10, they'll be finished at 10:30. And if they're finished at 10:30 before you get here, you are TOAST. You cannot take the final. And that's going to sink your grade. So just make it, just and totally engrave it in your mind, 10 a.m. on April 30th, and you'll be good. Now, we're going to have a little bit more about grade and estimating your grade. I know a bunch of you have messaged me about it, and I got to round up. The thing that's hanging me up is the iClicker data. It's been all blooped up for my other section, and so I'm kind of paranoid about it. So I got to look at the clicker data, make sure it's absolutely accurate. But I hope to give you more about that on Thursday. All right. And I believe, and the uh, the withdrawal date is Friday, isn't it?
No, it's
Tomorrow, the 20th. Ooh. So maybe I'll have to accelerate that and get everybody's. Oh my goodness. Nothing like a little pressure. All right, I'll try to get this done before Thursday, by tonight or tomorrow. All right, now I want to go over the calendar for the remainder of the semester, and you can, you know, uh, copy this or just, review it in YouTube. Here's this week, lecture 19. That's today, and we have office hours tomorrow, lecture 20 on Thursday. Uh, and then we have next week another 2 lectures. Next week we'll probably be talking about springs, oscillation. We're going to be talking about thermal physics this week. And then the week after that, we'll be talking about electricity and magnetism. And that is going to be, that's going to lead up to lecture 25, which is exam 3. So we'll have a lot of different topics: thermal energy, springs, oscillating systems, and then electromagnetism. And then that week, we probably will hold that lecture Thursday, lecture 26, because we're going to be working on the periodic table and quantum physics. And so that week, and then the final week of the semester, is what I like to call the target week. We want to be hitting the periodic table there, okay, and quantum physics, and we're on pace to do that. All right, so we're looking good for that, and so you can just kind of see the layout topic-wise and schedule-wise. Now, the week after that, we have study day on Tuesday, and then I think I'm going to have mega office hours on Wednesday of exam week. And Jazz, do you have any idea on your study Union? All right, so they're gonna Yaz is gonna have a big mega review for SI, a big SI mega review as well in the student union, and those are really, it's like going to be 2 hours, and they're really helpful. And but we don't know what that is yet. So I'll try to schedule it my office hours so they don't overlap with the SI mega review and study union. Right. Then the Tuesday after that, we have the final exam. So we got a lot of stuff coming up. Now we're going to talk about physics now. One last thing from the whole just superstructure of momentum and energy. We could speak an entire semester. We could speak years about momentum and energy and not be finished. I want to talk about something called a phase diagram, and it's an abstract diagram, which we have used abstract diagrams before, i.e., the velocity graph. It's not something you can take a photograph of, but it's something that you can make, and it helps you think. And that's the same thing with a phase diagram. Now, the phase diagram is a way of mapping out the position on the horizontal axis and then the corresponding momentum on the vertical axis. Now, this one, and that's called phase space. It's not an XY graph paper space where you can actually make a map or a diagram of something. You can make a diagram of a dynamical system, but now you're graphing up momentum on a vertical axis. So this is P subscript X, the X component of the momentum, whatever it happens to be, and the X coordinate, whatever that happens to be. So if you know both of those, you know a whole lot about that system. You figure out forces, accelerations, all kinds of stuff. Now, one nice thing is that it's completely abstract, but in phase space, the motion can be representative. For instance, if you have uniform circular motion, so in XY graph paper, a perfect circle, that's nice. But in phase space, it's going to look like maybe a circle or maybe an ellipse, depending on the scales that you have. All right. So this diagram over here would represent some kind of a periodic motion on a periodic basis. For instance, a uniform circular motion. And the important thing is that the area, again, for this particular abstract diagram has a physical interpretation. Now remember, the velocity graph that we started with the first week or so of the semester, that had an interpretation. The area of that, between the graph and the time axis is the amount of distance that you've traveled for that time interval that you're looking at. Right? And we use that to derive, like 1/2 AT squared, 1/2 GT squared for something in free fall. And it's not a distance interpretation here, but if you look at the units, okay, the horizontal unit is in meters, so this ellipse has a width in meters, and it has a height in kilogram meter per second. In other words, the units of momentum. So what that means is that the area, width times height, is equal to kilogram meter squared per second, and that's angular momentum. And that, my wonderful students, will become extremely important for us when we get to the periodic table, believe it or not. Because the electrons in an atom, when you map them out in a phase diagram, the interpretation of the area of the ellipse is actually at the deepest level of quantum physics. So we're actually doing this. Regular physicists do this for any kind of an oscillating system, and in fact, cardiologists use phase diagrams a little bit differently than this, but they use phase diagrams to map out a patient's heartbeat. Is their heartbeat regular? Or is it chaotic? Is it in fibrillation? Or is it, does it have some unusual shape when you map it out in a phase diagram, and they can tell a lot from that. But the most important thing is its application to quantum physics, the periodic table. So here's a blow up. All right, and the vertical axis is the momentum in the x direction. So so it goes coordinate by component. In other words, choose any coordinate in your system on your graph paper, and then take the matching component of momentum that goes along that axis. And that's what you put into a phase diagram. Now you can do a really abstract phase space with multiple dimensions, okay? But this is the easiest one to graph. So in this graph, you might have, an ellipse, and this position over here on the far left, that would be the leftmost x coordinate, right? And that tells you, so if you think of a spring going back and forth, boing, like this, back and forth, the spring will go so far to the left, and then it'll start cutting back to the right. And then it'll go so far to the right, okay, that's out here, and it'll start cutting back to the left. In other words, a spring is going to be going around and around on this ellipse. So this ellipse doesn't just have a shape, it has a sense of time embedded in the ellipse, or the arrow of time, the direction of time is encoded into the ellipse. Now, the vertical dimension, maximum momentum value up here, like 4.5 kilogram meters per second or something like that. And then it's opposite down here. The opposite of that, if it's symmetric, this will be negative 4.5 kilogram meters per second. All right. And so that's kind of the basic anatomy of a phase diagram. And the interesting thing is the width. If you take the width from the origin out to the maximum right or out to the maximum left, that's called the semi-major axis. And then if you take the height from the origin up to P max or down to negative P max, that's the semi-minor axis. So you have these two dimensions basically. If you have those two, you can graph out the entire ellipse. And the area of an ellipse is really, really easy. It's the formula for the area of an ellipse is this: pi times the semi-major axis times the semi-minor axis. Okay, so that would be pi times x r times p max, for instance. And you would use absolute value if you're going to use minus p max, and absolute value if you're going to use xl for your calculation. But p max and xr do the job just fine. And if it's an oscillating and periodic system, if it's going to be symmetric like this, you have the area. And hey, you guys, an ellipse like this, pi times semi-major times semi-minor. If you compare this to a circle is an ellipse, but it has the same semi-major as semi-minor axis. The distance from the center to any point on the circle is the same. So semi-major is equal to the radius, semi-minor is equal to the radius, and we all know the area of a circle, pi times r, pi r squared. And so this is consistent with circles. Now remember, this is not a snapshot, okay? And but the area does have an interpretation, as I mentioned, angular momentum, right? And so you can actually, if you understand this, you can actually get an oscillation frequency. If it's an electromagnetic system, you can figure out a wavelength, the electromagnetic waves that are generated. You can get a whole lot of this, and it's going to be really important for us when we study the periodic table. All right. So that's just a little bit of a thing. We'll be getting back to phase diagrams in target week, right? Because it's going to make a whole lot of sense about what the periodic table is doing. if we figure that out. Now I want to turn to thermal physics. And here's a thermal system that we see a lot. Can you imagine? I've seen thunderstorms. One time I drove from Fort Lauderdale uh, up to, and back to Orlando by way of Clewiston and Lake Okeechobee and stuff. And so we were out there on the Everglades, and oh my goodness, you could see these big storms, not as dramatic as this one, but pretty dramatic even so, from miles away. And that's basically a big thermal convection system. So we'll be talking about that probably tomorrow, probably Thursday. So let's get going with some of the basic concepts that we're going to talk about. And we'll start with James Prescott Joule. Now, one of the things that he did, he's famous, we named the unit of energy after him. He was curious about the thermal equivalent of energy and work. So what he did was he took a device and he stirred up water with it. Here's the device. And this isn't the device that he used, but it's kind of a idealized view of it. A pail of water, and it had some paddle wheels in it. And he could turn the paddle wheels by letting this little weight over here drop some delta Y. So as that weight dropped from Y equals 1.5 meters down to the floor, it lost potential energy, and the kinetic energy went into the paddles, all right? And they added energy to the water. And so his guess was that the energy added would correlate to the temperature or the change in temperature. And that's why over on this device you have a little thermometer. And he figured it out. And what it does is leads to the kinetic theory of matter, which is that a fluid like water or like the atmosphere has zillions and zillions of atoms and molecules that we cannot see. But each of them obeys Newton's laws of motion. So F equals ma, 1/2 mv squared, P equals mv, even angular momentum. All those things are possessed by each atom or molecule in the fluid. All right? And the average kinetic, and in the kinetic theory, one of the results is that the temperature on the thermometer is proportional to the average kinetic energy. So you have to use trig and calculus out the wazoo and stats to calculate this relationship. But it turns out to be fairly simple. That the average, doing trig, calculus, and stats of 1/2 mv squared for every atom or molecule in the fluid is proportional to some temperature on your thermometer. All right, now we have Fahrenheit, we have Celsius, and I'm going to be telling you about another temperature scale that we use called the Kelvin scale. But basically, that's one of the key findings of the kinetic theory, that the kinetic energy average for the fluid is proportional to, and the kinetic energy of things we cannot see corresponds to a single temperature that we can see that is macroscopically measurable with a thermometer. Okay, so another topic that we're going to talk about is thermal equilibrium. So if two things have different temperatures and they're in contact, so your hand with a can of Pepsi that's just out of the refrigerator, okay? Pepsi's cold, your hand is 98.6 Fahrenheit, so your hand's going to get cooled off, and the Pepsi's going to get warmed up, right? That's because they're not at thermal equilibrium. And it also is because heat is a form of energy that can be transported from one substance to another. All right, so you take an ice cube out of the fridge, out of the freezer, just put it in your hand, and in a few minutes it's going to start melting, right? Because heat from your hand and from the air is going to heat up the ice to the point of the freezing point and then above that. And as soon as it gets above that, you've got some liquid water instead of solid water. And that brings us to this last topic. The different elements and molecules cool up and heat up differently. Okay, so, and that leads us to the idea of phases of matter. For instance, liquid water, and we're going to finish today with a calculation about turning ice into water. Liquid water is fairly easy to, is fairly difficult to heat up, and solid water, known as ice, is a little bit tougher to heat up. All right, so we're going to cover that as well. But before we do any of that, we want to introduce the Kelvin temperature scale. So let's talk about this. Now, the Kelvin temperature scale is a metric scale. It's based on Celsius. But unlike the Celsius scale, which basically goes from 0 to 100, here's Celsius over here on the right. Boiling water at 100 Celsius, freezing water at 0 Celsius, that's nice for the Celsius. But the Kelvin temperature scale does not use the boiling point of water for its 0 point. It uses something called absolute zero. And this is the conventionally considered point at which, molecules stop buzzing around. All right. Okay, so the kinetic theory of matter says, okay, when you have a temperature, you've got an average kinetic energy. So if you have 0 temperature, that means your kinetic energy average is 0. Right now, the problem with that is that in quantum physics, nothing ever stops oscillating. There's always quantum waves waving. Okay, but it's better to say, for that reason, that the 0 point, known as absolute zero, is the thermal point from which no more work can be extracted. So if you have 0.001 Kelvin temperature, you can still use that to, power a steam engine. Well, it won't be steam, but I mean some kind of a heat engine. All right. And what heat engines do is they extract a little bit of motion from the expanding gas or coolant, if it's an air conditioner, and that does a little bit of work. But at absolute zero, you can't do anything. You can't get anything, any useful work out of that. So that's the theoretical description. But colloquially, yeah, where all molecular motion ceases, it's absolute zero. Now, here's the specs for the temperature scale. 0 in the Kelvin scale is minus 273 on Celsius. Right now, the degree sizes are still the same. There's still 100 kelvins between boiling and freezing of liquid water. But the numbers are different. So 273 Kelvin is the freezing point. Now that's 0 on Celsius, but in the Kelvin scale, we call it 273. And we call absolute zero, that's what we call 0 at the Kelvin scale. In the Celsius scale, it's minus 273. And according to this diagram, minus 273.15. Now, boiling point is 100 kelvins above that, so 373. All right. And going back and forth, you're either adding 273 or subtracting 273. So if you have a Celsius temperature, just add 273, and bam, that's your Kelvin temperature. All right. Now I'm going to give you an iClicker question here, just kind of a little mini workout, but that was my phone, I guess. Any questions before we proceed? Raise your hand if you learned about the Kelvin scale in like high school or middle school. Okay, a few of you. All right. So the rest of you, this will be news. That's good. All right, let's do a simple conversion. Oops, my computer's off here. Hold on. Okay, here we go. Go ahead and start. What's 20 degrees Celsius in the Kelvin scale? Mm, doing good. 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Well, we have a lot of people absent today. Okay. But you guys did good. 82% of you got this answer correct. 293. So basically, your theory is, um, whatever Celsius is, just at 273, and that's your Kelvin temperature. All right. Now, we're going to go through some other factors about Kelvin temperatures, and this is another uh, clicker question. Read these and make a judgment about what you think is an advantage to the Kelvin scale. And I'll let you think about this for a minute. Okay, 20 seconds. And I'm going to show you the results here. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, now I'm going to show you this. Here's the distribution. Now, the correct answer is A, but a bunch of you chose B and C. Now, let's go over that. B is not correct because multiplying out to absolute zero is not really what you do. Most of the time with temperatures, um, you're taking a delta T, you're taking a change in the temperature. And for us, that's important. When calculating the temperature, the Kelvin is easier because it's larger than the Celsius degree. That is incorrect. The Kelvin is the same size as a Celsius degree. You just start counting them at absolute zero instead of at freezing point of water. So that one is incorrect. The basic advantage is this, and it's one of the reasons that the Kelvin temperature is so useful, because it correlates to the fact that average kinetic energy is always positive or zero. You never get a negative kinetic energy. So if you have an average, it's either going to be zero or it's going to be positive, and that's where the Kelvin temperature comes in nice, because I told you before that the average kinetic energy of a gas or a fluid of some kind is proportional to the temperature. You can do that with Fahrenheit and you can do it with Celsius, but you have to subtract from absolute zero and stuff. And so it's much trickier in Fahrenheit or Celsius. But in in Kelvin scale, you just multiply a small number times the temperature in the Kelvin scale, and bang, you have your average kinetic energy. It's really sweet. All right, so it works out nicely. Now, I want to give you some more information about hot uh, temperature and color in terms of heat phenomena. All right, now, here's an image that is a few years old. This is an actual image of the face of a star that is close enough and big enough that we can actually make out the features of it. This is called Betelgeuse. Now, Betelgeuse, if I remember correctly, is the right shoulder of the constellation Orion. Now, Orion is up, I think it's up after midnight now this time of year, so you won't be able to see it much longer. You got to be up late. But if you know your Orion, the 3 stars in the belt of Orion, then you can figure out, he's standing up and he's got 2 shoulders and he's got 2 knees and stuff like that. Anyway, so Betelgeuse is a red supergiant, and we know that the color of the surface of Betelgeuse, it's kind of a reddish orange, as you can see, and it's got some, let me get my cursor over here. It's got some spots. These are actually sunspots. They're ginormous on the surface of Betelgeuse. Now, very few stars can we actually make out any features. I mean, the sun, of course, we can make out all kinds of features on it. But most stars are just a little point of light. We can't really make it. But this one is so big and so close, we can see some features. Now, it's not much detail. But the color is important. That the color of Betelgeuse, kind of reddish orange, tells us that the surface temperature is maybe 3,000 Kelvin, right? And so the reddish orange color tells us the basic temperature. Okay, now here's a globular cluster called M13. And if you look at this carefully, you can see a lot more bluish stars in there. Now, blue stars are hotter. So these might be up surface temperature 8,000. Our star is about 5,800. Do you know what the color of our star is? The sun? It's actually kind of greenish yellow. Yeah. Now we see it as just like a white circle up in the sky, but it produces a lot of, sunlight and stuff. But actually, if you were an alien on another planet, and like if you're an alien orbiting Betelgeuse, so you're used to a red star, you'd look at Earth and think, oh, that's kind of a greenish yellow star. Okay, but for us it looks normal because our eyes are designed for that. Anyway, so blue stars are going to be hotter. You can see some red stuff in here too. Okay, there's some reddish stars in there. All right, and on YouTube this will look even better. Although this display is pretty nice. That's got a lot more blue. And so astronomers, one of the first things they do, they put they put the starlight from a star and they put it through a device called a diffraction grating. And a diffraction grating basically does the same thing that a prism does. It splits up sunlight or starlight into its colors, into a rainbow. So if you have a lot of energy, and then what it does is it measures how much energy is in the red, how much energy is in the orange, how much energy is in the yellow, green, blue, indigo, and violet, all the colors. And also infrared and ultraviolet. We can, we have diffraction gratings to split the starlight into that. So these blue stars probably generate an awful lot of ultraviolet as well. Right now, you can't see ultraviolet with our eyes, but we have detectors for it. Infrared too. We can't really see infrared unless we have infrared goggles and whatnot. But astronomers do that all the time. So the basic idea is, my wonderful students, coolest, infrared, red, orange, yellow, green, blue, indigo, violet. Violet is hottest, and then ultraviolet even hotter than that. Now, let me give you an example of a star that we all see every day, the sun. This is a false color image in ultraviolet, and the wavelength is 17.1 nanometers. And it actually maps out the upper atmosphere of the sun, where the temperature is about 1 million Kelvin. So if you have a Kelvin temperature up in the area of 1 million, you're going to be putting out a lot of ultraviolet at this wavelength, 17.1 nanometers. Now, what is a nanometer? That's a billionth of a meter, 10 to the minus 9 meters. Okay, and that's a really short wavelength, and that corresponds to ultraviolet. Now, this is a false color. The sun doesn't look this color. So what they do is they measure the intensity of the ultraviolet, and wherever it's really, really bright, they make it somewhere between a blue and a light blue or white. So some of the, like right over here on the right side, you see a bunch of really almost whitish spots. Those are sunspots affecting the upper atmosphere, and it's really, really hot there. So you get a lot of ultraviolet. Okay, so this is actually, this is from last semester. So 12/20, let's see, 13/23 on October 22nd last semester. All right, and you can look, there's a website, I'll show it to you on Thursday, where you can look up you can look up this picture every day, several times a day, if you want to look at it. So the whole idea of temperature and color is important, and we're going to keep that in mind as we go. Now, I want to get down to the nitty-gritty of heating and cooling, and we're going to do a calculation here, for the last, 20 minutes or so of class. All right, we're going pretty fast today, but I don't want to go too fast. All right, so here we go. We're now going to talk about specific heat. The specific heat is a property of a material. Could be liquid water, could be solid water, could be a metal, could be a biological substance like wood. And basically what it does is it tells you how easy it is to heat up or cool down a given substance. Now, liquid water defines everything. So this is part of the metric system. A calorie is a unit of energy, and it is the amount of energy that it takes to raise 1 gram of liquid water by 1 Kelvin, right, in Paris, France, because it's a metric system. So 1 calorie of energy from sunlight or from any other heat transport method, you turn on a butane, propane burner, from Strickland propane or whatnot, and you heat up your ice or your liquid water by 1 Kelvin, and every gram requires 1 calorie. Side note, this is known as the gram calorie or the thermal calorie. The food calorie is 1,000 of these babies. Okay, a food calorie is usually in an equation uses a capital C. Now, I always write out the word CAL in lowercase to represent this kind of a calorie. And it's, to convert from little calories to food calories is just multiply by 1,000 or divide by 1,000, depending on which way you want to go, right? Chemistry department would call a food calorie a kcal. In other words, K meaning 1,000, or a kilocalorie. Raise your hand if you've ever had a chemistry class and you did kcals, and a few of you, yeah. So that's a food calorie. But and just as an additional side note, when we're doing these calculations of heating up substances and melting and stuff like that, we're going to be doing almost always grams, calories, instead of kilograms and joules. You can do everything in kilograms and joules if you want, but I'm going to do everything in calories. It's a little bit easier to understand, I think. So what you would say for water, liquid water is this: the specific heat of liquid water is 1 calorie per gram per Kelvin. And the way that you would write that down in a little equation is C equals 1.00 calorie per gram Kelvin. Now, some websites and textbooks will have calorie per gram degrees Celsius, but a degree Celsius and a Kelvin are the same. All right, so that shouldn't be an issue. But I always go calories, grams, and kelvins because kelvins are what we use in astrophysics, and so you know we don't dibble around. And we're not gonna. And just so you know, in case you hate converting from Celsius to Fahrenheit and Fahrenheit to Celsius and all that rigmarole, we're not going to do jack with that. Not at all. About the only thing we're going to do is like the one we just did a few minutes ago, where we went from Celsius to Kelvin, and that's it. So on exam 3, you might have one question. Okay, room temperature is 20. What's the in Celsius? What's the Kelvin temperature? And that'll be it, just to remind you of what the 273 business is. But so we're not going to be doing anything in Fahrenheit for sure, and just a little bit of a flavor of Celsius because it is related to Kelvin. But everything important is going to be in kelvins. Now, another substance like solid water, also known as ice, it has a different specific heat. It's easier to heat up ice. It only takes 0.50 calories per gram Kelvin. So what you would say is, if I want to heat up water, liquid water, it's a little tougher. I need a full calorie to bring it up by 1 Kelvin, But if I have a gram of ice, all I need is a half calorie to bring it up by 1 Kelvin. So it's a little bit easier which, it doesn't make sense, does it? Because ice, that's supposed to be cold, right? But it's easier to heat up. And that's the way it is with a lot of substances. Okay, so you would write down C equals 0.50 calories per gram Kelvin for solid water, i.e. for ice. Now, here's a question for you. What's the difference between liquid phase of H2O and its solid phase? Right, liquid water and solid water. Well, the difference is the crystalline structure of water in the solid phase. Ice crystals, snowflakes, they say, always have a hexagonal symmetry, the beautiful designs, Mother Nature makes in hexagonal shape. And those crystalline bonds are fairly tough, all right? They're tough enough to hold as that snowflake drifts down from the upper atmosphere and settles on the ground. Although here in Florida, they don't settle on the ground at all. They always, melt on the way down. I think there's probably snow in these. Actually, anytime you see, what do you call those things? Hailstones. If you've ever been in a thunderstorm where it hails, who's ever seen a really big hailstone? Okay, what was the biggest hail? How big was it? Oh my goodness, yeah, Kansas. That's a big hailstones out there, and that's ice. It's ice, and so I'm sure that inside that cloud were snowflakes as well, but then they conglomerate into ice, stones of ice, and fall as hail. And if they don't melt on the way and out in Kansas, a lot of times you saw off in the distance, you saw thunderstorms and the rain was coming down, but it evaporated before it hit the ground, right? It's kind of like tentacles dribbling down from the bottom of the thundercloud, but it doesn't. Did you ever see that? Well, it may be different in Kansas, but out in Montana, it's a lot drier out in Montana, and you see that all the time. You see the rain coming down from the cloud, but it never reaches the ground because it evaporates so quickly because it's so dry in Montana. I guess Kansas maybe is different, but all right. So the difference between liquid and solid phase is they have a different kinetic energy. All right, so the temperature above 273 Kelvin or below it means, okay, if you're at like 272, you're ice and you have a much lower kinetic energy. If you're at 274, you're liquid and you have a higher kinetic energy on average, right? And so the crystalline bonds below 273, you know what that is? That's electrical potential energy, EPE. Go ahead and write that down. In other words, these are the intermolecular forces, hydrogen bonding, if you will, for the water molecules that form the beautiful hexagonal shapes in an ice crystal. Now those things are important. They represent stored energy. If you want to turn a snowflake into a drop of water, you have to break those bonds. And the way that you do that is by adding heat energy. You put the snowflake in the palm of your hand, and the heat from your hand will melt the snowflake, all right, or the ice cube, all right. So the process of melting requires energy as well. So you need energy. You need half a calorie to raise a gram of ice by a Kelvin. You need 1 full calorie to raise a gram of liquid water by a Kelvin. And to melt a gram of solid water and turn it into a gram of liquid water, you got to bust up those intermolecular bonds. And that takes energy too. So that process of freezing, melting, melting requires adding energy to break up the bonds at the freezing point. And freezing means extracting energy, by a refrigeration process at 273 Kelvin. And that will allow the bonds to form. If there's too much kinetic energy, the water molecules, they'll try to bond, but they won't stay bonded because they're flying around too fast. But at 273, that's where you can get them to stick and form those beautiful hexagonal bonds. Now, other substances, you just look it up on a table. So let's go ahead and jot down a few here. Right? There's some melting and freezing points. Go ahead and jot these down. Water, copper, and aluminum. And I'm going to ask you a question about these. So make sure you jot these down for the next clicker question. All right. The specific heat of solid H2O, and these are just solids now. We already know what liquid water is. Okay, so for solid H2O, 0.5 calories per gram Kelvin, melting and freezing point 273 Kelvin. Copper, 0.0923 calories per gram Kelvin for the specific heat. And melting and freezing point, you don't really think about that as freezing for copper, but that's what you could call it that. It's 1358 Kelvin, so that's pretty high melting point. Aluminum is not quite as high of a melting point, 933 Kelvin. It's still pretty high. It's totally hot, but it's not as hot as copper. But it has a specific heat of 0.215 calories per gram Kelvin. All right. So let me ask you, so if you've got these jotted down in your notebook, let's go ahead and do a clicker question. And just to see if you savvy this concept of specific heat and what specific heat tells you. All right. So let me get the question going here. Okay. 1 gram of this solid substance is easier to heat up by 1 Kelvin. Which one is it? A, B, or C? D is not an answer. Good. What is that anyways? Is that a macchiato or something like that? Looks like almost like dessert. Okay, 15 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, and let's take a look. Get my cursor over here. We have a little bit of a mixture of results. There's a bunch for each of the three options. All right. Now, the correct one is copper. Now, why is that? Here's the reason, and go back to your notes. Copper is easier to heat up gram for gram because copper has the smallest of the specific heats in this middle column, 0.0923. So that means if you have a gram of copper, you just need 0.0923 calories to boost it up by a Kelvin. Whereas solid water, you need a half a calorie. And down here for aluminum, you need 0.215. So copper is the easiest one to heat up. Now, let me give you a look at an exam from the distant past. Here's a table that I gave the students on a recent exam, like exam 3 type exam. And you can see on it that I have specific heat and I have the melting point. And then the fourth column is something called latent heat. Now, latent heat is what we call the amount of energy per gram to break the crystalline bonds or metallic bonds and let it form a liquid. All right, so going from solid gold to liquid gold, molten gold, you're at the jewelry store and you're melting some gold so that you can make a nice ring or something like that. You need 15 calories per gram to melt it. And what temperature do you have to be at? You have to be at 1337. And the gold will all stay at that temperature till all of it's melted. Same with water. Water will all stay at 273. And you see this all the time. Ice water. Ice water. If you have a styrofoam cup of ice water and a good lid, it'll stay. It won't. The ice in there won't melt very much because it's not getting any heat. It's happy to be at 32 Fahrenheit, 0 Celsius, 273 Kelvin, right? The temperature of ice water. The laboratories use that all the time because H2O ice and liquid are particularly stable if you have a good insulated container. But if you want to melt a gram of ice and turn it into a gram of liquid at 273 without raising the temperature, just busting up the crystalline bonds, 80 calories. All right. And if you want to, do the same thing for silver, 26.5, aluminum, blah, blah. And, and it's all related to the melting point. So if I give you a latent heat, but I don't give you a melting point, then you're kind of out to lunch. You don't know what temperature you got to work at. All right. So let me ask you this. On this table, which substance and I don't have a clicker question, but raise your hand if you can savvy the answer. Which substance, H2O ice, gold, silver, aluminum, is the toughest to break apart from solid into liquid? Which one is the toughest? Is your hand up? No? Yeah. Okay. Daniel.
Liquid water.
Incorrect. Liquid water is not the tough. It's tough. Yeah, liquid water is already a liquid. So you want to answer in terms of solid water. Which solid here is toughest to break up into a liquid? Gold is not. That's the easiest. Is not. That's not the hardest. Aluminum. Yeah, aluminum. 95. So solid water needs 80 calories to break up a gram of those crystalline bonds. But aluminum, and students, this is why aluminum is so hard to make, because aluminum requires a huge amount of heat to what they call smelt. Smelting aluminum is very, very energy intensive. It requires a lot of electricity to do it. So the answer here is aluminum bonds are toughest. Now that's on a gram for gram basis. Now here's the detail. Let me just make a side note, footnote to history. Gram for gram doesn't mean molecule for molecule or pair of molecules per pair of molecules, because there might be more H2O molecules per gram than there are for aluminum, right? Because an aluminum atom has a certain mass, and H2O, that's two hydrogens and an oxygen, definitely I think is lighter than aluminum. So on the basis of bond for bond between any two waters and any two aluminums, it might be a different story. But on the terms of gram for gram, matter of fact, gold might be toughest to break the bonds because gold is really heavy. So 1 gram of gold, you don't have a whole lot of gold. 1 gram of aluminum is much lighter. So you got a lot more aluminum atoms in a gram of aluminum than you have a gram of gold. So you can work it out on that basis. But for us, in our scale of working, we're going to be working with grams and so forth, the calories. Latent heat is on a gram for gram basis is righteous. Now, let's take a few minutes to do a calculation. This is the famous heat melt heat problem that every semester I ask my students to be able to, like stopping distance, stopping time, drop speed, drop time. All those are, classic brain burners that I like to ask students every semester. And here's another one. So what we're going to do is make a cup of tea for a polar bear up north. And here's our problem. The polar bear's got 400 grams of water, and they want to make some tea. All right, so they want to get it up to the boiling point. And then they pour it out, and then they, make their tea. All right, so it starts at 268 Kelvin. So that's below the freezing point of water. And we want to get it up right to 373, the boiling point of water. All right, so there's our task. All right, and so let's do this, heat, melt, heat. So 400 grams of ice, and let's just jot down some of the stuff we know. Latent heat of melting for H2O is 396 kilojoules per kilogram. Now we could do it in that, but let's do calories per gram, 80. That's easier to use. But yeah, I mean, you could do, as I said, you could do kilojoules per kilogram if you want. But we're going to use 80 calories per gram. Okay, and the specific heats. We have ice, we want to melt it, and then we've got liquid water. So we have two different specific heats. All right, 0.50 calories per gram Kelvin for ice. And then we have 1.00 calories per gram Kelvin for liquid water. Okay, so the ice is going to be easier to heat up, and the liquid water is going to be a little tougher to heat up. But between those two, we got to bust up all the ice and turn it into liquid. So we got a 3-part process here. All right, so let's look at our strategy. Here's strategy number 1. We're going to heat the ice from initial temperature 268 up to 273. All right, so that's, and we're going to heat it up by 5 kelvins. All right, so that's a delta T, but there's another delta T after we melt it. All right, We're going to melt all of it at 273. Right? So while we're going to heat it up 5 kelvins, now it's at 273. And then every calorie we add at 273 will go into melting ice. The ice and water mixture will still be 273 until all the ice is melted. And when you got all liquid water 273, the next calorie you add to it, by sunlight or propane burner or whatever it happens to be, that next calorie is going to start raising the temperature. So it goes heat, melt, all of it, and then heat some more as a liquid. So here's the liquid heating up procedure. From the freezing point to the target temperature, 373. Now that's a heat up of plus 100 Kelvin. So that's a little bit bigger of a delta T. So we got two delta T's here. All right. And in between the two heating procedures, we got the melting procedure. So that's why I call this heat, melt, heat. All right, here we go. Let's go and start. Can I turn the page? I'm not permitted to. I'm not permitted to turn my page. Okay. Yeah. So this is just kind of we're just kind of jotting down the specs. So our strategy is to heat and then melt. And in the melting, remember, it stays at 273. Now, if you have copper, it stays at the melting point of copper, so, or if you're doing paraffin wax, that's going to have a different heating and melting point, okay? But if it's water, it all stays at 273 until all of it is liquid. And then it starts heating up if you add more energy. All right, here we go. So here are the two equations that we're going to use. The first one, Q, tells you the amount of energy. So Q is a symbol for thermal energy. MC delta T. Now what is that? That is the mass of your sample that you're heating up or cooling. C is the specific heat, and delta T is your delta T. How many kelvins are you rising the temperature? So for the ice here, delta T is 5 kelvins. And for both liquid and ice, the mass M is 400 grams. But the specific heat is different. So we have this top equation, Q equals MC delta T, the heat up equation, we're going to use it twice. Once for ice and once for liquid water. Now in between, we have the melting equation. So that's what this says is the thermal energy to melt a certain amount of mass, for us 400 grams, is just the mass times whatever the latent heat of fusion is. And fusion means fusing into a solid. So that's why it's called. You could call it the latent heat of freezing if you want. So basically that means and that's what latent heat says. For every gram that you have, you need 80 calories to bust it up into a liquid. So you multiply by the number of grams that you have. That's M in this equation. So that's the melting equation. So we have two heating equations and one melting, and we're going to use the melting equation once. All right? And here are my temperatures. 268, initial temperature. Melting point, 273. Final temperature, 373. So now when you guys are doing your homework tonight, oh, did I say homework? Yes. So lovely and so, you guys had 2 weeks off from homework, so you better get some homework tonight. So you might have just read the problem for different initial and final temperatures. The freezing point doesn't change. That's always going to, you're going to be doing heat, melt, heat for water. You're going to be helping the polar bears or the penguins down in Antarctica or something like that make some tea or do the dishes or something. So it's always going to have 273, but the initial and final temperatures might be different. So your delta T's are plus 5 and plus 100, as I mentioned earlier. Now, here's your first heat up equation, all right? The mass, mc delta T, mass 400 grams. Now, this is ice. So you put in the middle parentheses, you put in the specific heat of ice, 0.50 calories per gram Kelvin. And then you put the amount of delta T, 5K, 5 kelvins, all right? Now look at all the stuff that cancels. Kelvins cancels from the third parenthesis and the denominator of the second parenthesis. And then grams cancel from the first parenthesis and the denominator of the second parenthesis. So all you're left with is calories. And it works out to be 1,000. All right? So that's pretty nice. Right? So that's how much energy you need to raise 400 grams by 5 Kelvin. Now let's do the second heating equation. And you do them in any order you want. We'll just do 2 heating equations. Okay, so we still have 400 grams, but now it's liquid water. We've melted all of it, and we haven't calculated the melting, but we will in a second. But we're doing the liquid water here. And we're going from 273 up to 373. So this third parenthesis is 100 Kelvin. All right. And notice that I have a much bigger delta T, 20 times bigger, and I have a bigger specific heat. Because remember, specific heat now for liquid water, heatable liquid water, 1.00 calories per gram Kelvin. So total is 40,000. So between those two, I have 41,000. But I haven't used the melting equation yet. So let's do that. Here's Q for that. And just take the number of grams you have, and each one of them requires 80, so 400 times 80. Bing. 32,000 calories. All right. So now the total heat budget, and that's the terminology that I usually use on a heat melt heat problem, is 73,000. 41 plus 32 is 73. All right, so here's your answer. 73,000 calories. And for us to help the polar bear make a cup of tea, so you have to say to yourself, all right, do I have that much energy left in my propane tank? Or do I have to go switch out, get a new propane tank? Now, this is not a huge amount of calories. It's a fairly small, it's not even a liter of water. You know what it's like? It's not even a bottle of water, 20-ounce bottle of water. So not even that. So it doesn't require a lot of propane. But I mean, if you're out on a backpacking trip and you're trying to make some tea and you're up in Antarctic or you're up in the North Pole, you have a little camping stove and a little butane or propane container. And if it's out, you can't make your tea water. So you got to know how much you've got in there. So let me pause for questions. And we'll just go through this again if we have to. Any questions? Here's the temperatures. Yeah.
In the latent heat, the last one that you did, you got
Yeah.
80 calories.
80 calories per gram. Yeah. Let's go down to that equation. Yeah. Latent heat is 80. See down here? 80 calories per gram. Okay. So that means for every gram of ice that I've got, I have to add 80 calories to break it up from solid into liquid. All right, now I've got 400, so I just go 400 grams times 80 calories per gram. Grams cancel, and that tells me, how much to break those crystalline bonds and convert all the solid into all liquid.
Is the latent
Yeah, it's going to be on a table.
Okay.
Yeah, so you remember I had that slide on a table from a previous exam? Yeah,
You said 396
yeah.
kilojoules.
Yeah, that's if you're working kilojoules and stuff. But we're going to be working with 80. We're going to be working calories. So calories in grams and so forth. All right. Tiny homework. 11 tonight. Due Thursday, 10:30 a.m. You're dismissed.